Previously, we talked about the correlation coefficient and how we can use that value as a way to measure the linear relationship between x and y. Now what we're going to do is we're going to make predictions. We're going to use one variable to predict another. And we do that through the process of regression. Simple linear regression will find a straight line that best fits your data. And using that line, we'll be able to make predictions. This to me is one of the most fun parts of statistics. Building models, building functions to try to predict a variable using another variable. You can get to a lot of cool predictions using regression. So just so we get some stuff out of the way, we have two different types of variables. One which we call the response variable, which we denote as y. And it's called the response because we're trying to predict y. So at the end of the day, the metrics that we get are going to be predictions of the y value. Our responses will be in terms of y. Our x variable is going to be our explanatory variable. We're going to be using the x variable to try to explain what's going on with the y variable. And like we just talked about, we're going to be doing so by finding the line that best fits your data. So we have a bunch of different points, and we're going to try to find the line that best fits your data. What we need to think about, though, is how do we find that line? Right? Which line is better? The red line I just drew or this green line? Both of them seem to be doing really good jobs of representing that data. Which one is better? I can also throw in another line and another. I could just keep drawing lines that are doing a good job of representing your data. We want the best one, not an okay one, not a very good one, not an amazing one. We want the best line because that line will give us the best predictions. Okay, so where do we begin? How do we find that line? The method that we're going to be doing is called least squares regression. This is going to be the method that helps us find the best line that fits our data. Now, before we find that line, let's look at the equation for that line. For regression, we have slightly different notation than we do when finding a regular line. You may be used to the phrase y equals mx plus b. And this was the equation to find the line between points, a straight line. In statistics, we have something very close, but there are subtle differences. We'll notice that in our equation, there's a little hat on y. But we'll notice there wasn't a hat in our basic equation. That hat represents predicted values of y. We're going to be inserting values for x and spitting out values for y, predicted values of y, expected values of y. B0 represents your intercept, your y-intercept. And B1 represents your slope. This will be our statistical line that best fits our data and how we'll denote it. The method that we're going to use to find the line that best fits our data, like we just said, is called least squares regression. But specifically, it's going to try to minimize what we call the squared residuals. And these squared residuals are deviations from how far each observation is from the line. Let's see what I mean by this. Here's a demonstration to show you the concept of what line best fits our data. And it's quite simple on the surface. The line that best fits your data is the line that's closest to your points. So what we're going to do is look at something we call the residuals. A residual is how close your points are to the line. We'll notice as our residuals get bigger, those distances get bigger, the line that goes through your points is doing a worse job of representing them. As your line gets better and better and better, those distances get smaller. But we're not going to just look at the distance of how close a point is to the line. The reason being is that for the line that best fits your data, if you were to sum up these distances, your residuals, this point is above the line, so you'd have a positive number, below the line, a negative number, positive number above the line, and so on and so forth. If you were to sum up these distances, what do you think they'd sum to? 0. But that would only be true for the line that best fits your data. The sum of your residuals will be 0. And while that's great and something really important to keep note of, what it won't tell us is how close your points are to the line. If you just look at that sum and it's 0, well, are your points really close to the line or are they really far away from the line? We don't want to just sum those residuals because it will always equal 0 and not tell us how close your points are to the line. So instead what we do is we look at the square distances. And this green bar right here is summing up all of those squares. Actually, what we'll be doing in finding the line that best fits our data is we're going to be minimizing the sum of these square distances, the sum of these squared residuals. Because the line that best fits your data, not only will the residuals sum to 0, but they will give you the smallest sum of your squared distances. That will be the line that best fits your data. Just so we have it in our notes, here's a little recap of what we just went over. We want to find the line that minimizes the sum of your squared residuals. You can think of a residual as error, right? Because if we were to fit a line through our data, so here the line goes through the data, any point that is not on the line, like this one, your line isn't doing a perfect job of predicting. If a point was exactly on the line, well, your line is doing a perfect job of predicting it. So you can think of a residual as error because it's not perfectly on your line. This is why a residual is denoted as E. So EI represents an observations residual, where the E stands for error. Each point has their own residual. And we just said if we were to add up all those residuals, they would sum to 0. That is why we square them. Thus, our goal is to find the line that has the smallest sum of our squared residuals. This is our goal right here. Find the line that has the smallest sum of squared residuals.